let's go through. So we finished with mode last time, right? Am I correct in remembering that? Okay, awesome. So what we're going to do now is move on into, well, I guess any questions on, I went back through and just popped up that link. That link on the web page is just an easier way to go through and access stuff, right? What I'm going to do is I'll keep uploading lecture videos onto that YouTube channel, and then you can just access them from the front page. So I'm not sending out multiple links and stuff like that. But saw that people had gone through, accessed that. Any questions on on measures of central tendency, at least to what we've covered up to this point? Perfect. Okay, cool. So what we're going to do now is we're going to switch into variability. Like, this is an incredibly important concept that you want to have a good conceptual understanding of variability, what it is, how to think about it. Because, I don't know, means get all the showtime, but really it's variability that's a workhorse of our statistics. When we're talking about variability in general, so when I'm saying variability, I'm going to be talking about the extent to which scores in some distribution are either spread out or clustered together. Okay, if everybody in the distribution, if everybody in my sample has the same score, there's no variability. Everybody's identical, right? But if I have something that's super, super widespread, going to have a large degree of variability within that set. Can someone think about, someone give me an example of a variable that has a lot of variability? What do you think, Erica? Something that you can think of that people would vary quite a bit on. What's that? Maybe an IQ test. Okay, so we get some variability there, right? And that's something that's a nice kind of normal curve. So we get some variability in this. What if we were looking at, say, population of the U.S., something like income, right? That's going to be hugely variable. You're going to have people way, way on the high end of the scale. That's going to be a deeply skewed distribution. You're going to have people way on the opposite end of the scale. So that's going to be something that's sort of got a ton of variability, right? By contrast, if I took from my Psych 1000 class and I polled age of students in my Psych 1000 class, Robert, would I have a lot of variability in that? Not very much variability there. Yeah, why is that?
Because unless there's an outlier, or somebody in an extenuating situation or later age, then you're most likely all going to get like 18 and H3 roughly.
Exactly, right? I could have some non-traditional students who fall out there, but in general, I'm not going to have too much variability around my mean there, right? And so again, when you're thinking about variability and indices of variability, these are measures that are describing a distribution in terms of distance. Okay, they're going to tell us about how much distance do we expect from any two randomly selected scores from a distribution, or between any individual score and the mean, right? If we're using some means-based stuff. So if my measure of variability is quite large, you can expect, if I were to randomly grab two individuals from this sample, and I've got a lot of variability, I would expect those two scores on average to be quite different. Versus lower levels of variability, I go through and I'm pulling samples and samples and samples, and I'm expecting people to kind of hovering around the same value. Okay. Our variability, we can also think about this as telling us how well some individual score is going to represent my distribution as a whole. So Natalie, let's say I'm looking at levels of extroversion in, let's say, undergraduates, right? And I've got one, or we won't specify the population. Say I've pulled a sample from one population, and my variability measure is 5 for that measure, or for that distribution, and it's 20 for a different population, right? If I were to pull sample A has variability of 5, sample B has a variability of 20. If I pull a random score from each one of those distributions, For which distribution do I expect my randomly drawn score to be as close to representative of the rest of the group as the other, relative to the other?
The one with the variation of 5.
Yeah, right. Because with that one, everybody's kind of stacking pretty close. If I've got looking at age, right, and age is my Psych 1000 class, or age is everybody in Laramie, right? Any randomly selected person from my Psych 1000 group, much less variability. That person is probably more likely to be closer to the sort of the normative person in that than probably any randomly grabbed person from the population of Laramie in terms of age, right? And so when we're working with our models, if our mean value in the stuff that we're going to be looking at this semester, if our mean value is our best guess, right? This is the most representative value for our experimental group or our sort of group of interest or something like that. That level of variability tells me how much error to expect sort of around that. Because our mean is saying we're thinking that everybody's right about here. If I've got a lot of variability in my sample though, I don't know, I've gotten a lot of error. Yeah, this is the closest that I've got in terms of the actual value, but people kind of vary all over the place, right? Versus if I've got low level of variability, here's my mean, here's my most representative score, and people cluster pretty tightly around this, okay? So some different ways to think about variability in terms of distance, in terms of representativeness, relative to error if we're doing statistical modeling. I can't emphasize enough how important it is to have a good sense and understanding of variability and being able to think about this flexibly in a number of different ways. Okay. Questions on sort of variability overall? All right. So we've got, just like measures of central tendency, got a number of different ways that we can quantify variability. First, probably easiest, most straightforward measure of variability is going to be range. Okay, range is the distance between the largest score in the distribution, smallest score in the distribution. You can calculate this a couple of different ways. You can calculate range as the highest score minus the lowest score. You can calculate range as the highest score minus the lowest score plus 1. The asterisk here is just indicating that this is how SPSS calculates range. People get worked up about this. It probably matters 0, but it's one of those fun bar facts that people get really sassy about unnecessarily. But knowing that there's a couple different ways you can go through and calculate this. Limitations, range is fine. Range is a good kind of descriptive way to go through and talk about things. But the limitations is it's determined by 2 extreme values. Anything else in the set gets ignored. Okay, and this can start to throw us way off base in terms of what we understand in terms of the variability of a distribution. If we have distributions with outliers, right, like Robert was saying, let's say I got a mustache hair in my mouth or something like that, bugging me. Let's say I go through and I take a look at the age range of my Psych 1000 score. My range on that, last couple semesters back, I had a gentleman who was 80 years old in my class, right? And if I were to take the range of students' ages in my class, it would be super huge, right? But that's just because I've got one person. And so if I've got a distribution with an outlier, range can start to become misleading. And because range doesn't consider all scores in the distribution, starts to be not terribly accurate in terms of just by itself a measure of variability. Okay, so again, if we take a look here, let me see, Allie, tell me what's going on in this distribution if I'm talking about range.
Outlier, essentially, it's like very
Yeah.
different.
Is the range in these data very large or very small with this set?
Large.
It's very large, right? What happens if I get rid of that outlier on the end?
Then it becomes a lot smaller.
Yeah, right. And so if I just tell you, hey, the range of this distribution is 17, you're like, oh, wow, that's a lot, right? But if I cut that and I say the range is 4, that's a very different situation, right? And so range can be important, kind of just knowing the min and the max, but limits some pretty severe limitations in terms of this being a useful descriptive statistic for making inferences. Okay, but there are different types of range-based statistics that we'll go through and use. For those of you in Tara's assessment course, you'll probably be working with some of these other types of range statistics. All of us will be doing it when we're looking at box plots. Anybody familiar with quartile based statistics? Has anybody seen this before? Anybody? Okay, so essentially what we've got here is what we can do is we can take a distribution and section it up into quartiles. And the first quartile delineates the mark that outlines the lowest 25% of the distribution. So again, if we ordered everybody up in order, the score that cuts off the lower 25% of the distribution for the rest of the scores, that's going to be our first quartile. Our second quartile, this is going to find the center of the distribution. This is the 50th percentile, or our median, right? This is the score that splits it exactly in half. My second quartile, half of my scores are above it, other half of my scores are below it. It's the midpoint. Third quartile, this is the upper 25% of the distribution, right? This is the point at which 1/4 of my scores fall above this point, 3/4 fall below. Okay, so we can talk about these as first, second, and third quartiles. We can also, and you'll probably hear this discussed more often, talk about these as percentiles, right? If, Erica, you are talking about IQ, right? Do I want to be in the 30th percentile or the 70th percentile? Yeah, why? Exactly. Okay. And so we often hear about percentiles talked about in cognitive achievements and sort of testing and things like that, right? But if I'm in the 70th percentile, it means that I've done better than 70% of all the people, right? If I'm in the 30th percentile, it means I've done better than 30% of the people, right? And so if we've got something that's a normal distribution, we can start to understand kind of where these fall. We can also use these quartiles to calculate an interquartile range. Interquartile range is going to be the difference between the first and the third quartiles. Okay, you'll hear this called the middle 50. That means this is the cut points at which half of my sample the middle of my sample falls between this point and this point. Okay, so 50% of my scores falling in that interquartile range, and if you've got a nice normal distribution, you can start to make inferences on percentage likelihood of people falling outside of that. Again, if you've got a nice normal distribution. Okay. So people kind of getting a sense for these quartile statistics. Okay. And we'll be using these our box plots. We're going to use a lot of box plots this semester and next. These are metrics that our box plots are based off of. Okay. So again, we're looking at the interquartile range here of a nice normal distribution. We're seeing here a minimum value, here the maximum value, here's the median, here's the center, and then here's the cutoff that cuts off the bottom 25%, the upper 25% interquartile range. This is your middle 50. This captures the middle 50% of your sample, which in theory should be the collection of scores that are most representative of your distribution. Okay. All right. Limitations of interquartile range as a measure of variability. People will get upset because it cuts off too much of your data. Basically, it's only looking at the middle half of your data. Everything above, everything below starts to become sort of ignored, which starts to become problematic because in psychological science, a lot of the stuff that we're doing, we're actually interested in some of those people who are scoring maybe noticeably higher or noticeably lower than other people on some things. And so interquartile range is sort of an alternative metric, but some limitations there in terms of the number of scores that are ignored.
Can I ask you a question
Yeah.
about that? You showed us that graph just then. I'm looking at it too. So like the inner quartile. So you put all of your data like on this graph, right?
Mm-hmm.
And then what you look at is the inner quartile range. Like if I'm looking at this graph right here, and this is like 25%, 50%, and then 75%. That is like the first quartile, the second quartile, and the third quartile, right?
Yep.
Okay. And then that inner quartile, that stuff that's in between the 25th and 75th, is like what you're looking at.
Yep, the interquartile range there is going to say, let's say, well, let's just do this. Let's say the 25th or the first quartile is a score of 25, 75th quartile or the third quartile is a score of 75. What's my interquartile range?
It's between the 25 and the 75.
Yeah, what is that number?
Oh, 50.
50. There you go. That's my interquartile range, right?
Okay.
And when we look at this on graphs, you'll see in the box plot, you'll see where these are all mapped out. Okay. All right. So, range-based statistics are okay, but some limitations we want to, for our statistical models, be looking at some other stuff here. This is where our variance and standard deviation come in. Variance, standard deviation, these are going to be the most common forms of variability that we're likely to encounter in modern statistics. Again, cannot emphasize how important it is to have a good conceptualization of what these mean at a sort of meaningful level. Okay, standard deviation. We can loosely interpret your standard deviation as not quite, but approximately the average distance of any given score from the mean. Okay. So if I have a distribution and I just randomly go through and start drawing cases out of there and I take a look at those scores, my standard deviation is going to tell me about on average how far any randomly selected score is going to fall from the mean. Okay? So some scores are going to be really close to the mean, some scores are going to be really far away from the mean. On average, my standard deviation tells me if I just randomly select a person out of this distribution, on average, how far away from the mean are they going to be? Okay, and so we can think about this again, going back to this idea of representativeness or error, right? If I've got a really small standard deviation, I'm pretty confident that on average, any random person that I'm going to pull from a distribution is going to be pretty close to the mean. If I've got a huge standard deviation, boy, I don't know, I could pull somebody, they could be close to the mean, they could be way off base. It's kind of hard to tell, okay? So standard deviation is nice because it has some intuitive meaning that we can attach to it. Variance is going to be your second population moment. You'll hear this identified in statistics literature as sort of a second feature of a distribution. And your variance is so roughly the average squared distance from the mean. Okay, so if I took randomly drawn samples and I saw how far away they were from the mean, and I took that value and squared it, and then averaged it up, that would be my variance, okay? Variance doesn't hold as much intuitive meaning as our standard deviation does, but it's crucial for the calculation of our inferential statistics. It's going to be super, super meaningful, okay? So if I'm going to go through, Rachel, if I say, okay, Rachel, is there a scale that you work with closely in your research or that you're familiar with?
Trying to think of the name of it now. You put me on the spot. There's a self-injury scale.
Okay. And so if I told you, Rachel, oh, I've got a score on this distribution. I collected a sample on this self-injury scale, and the standard deviation is X. You would probably know what that means. So you say, okay, on average, this is about how far people are falling from the mean. If I gave you the variance, it's hard to know, right? To do that math in your head is not super intuitive, which is why for our descriptive statistics, we're generally reporting standard deviations, but important to know what variance is and the relationship between the two. Standard deviation is just the square root of the variance. If I take my variance, and I take the square root, or standard deviation is the square root of the variance. If I take my standard deviation, I take that to the second power, I square that, gives my variance, so it goes back and forth, right? One's just a more convenient metric than the other, okay? And so the one thing to be careful about our measures of variance and standard deviation is recognizing that the calculation of these statistics differs depending on whether or not we're talking about a population or whether or not we're talking about samples. Okay, so oops, there we go. So if we're going to calculate variance for the population, okay, Ariana, tell me what my population is. What population am I working with here?
Okay, I'm not completely sure, but is it just if I add up all of those numbers?
Yeah. Literally tell me any population and you will be right.
Oh, sorry. University undergrads.
Okay, university undergrads. That's a beautiful population. All right. So we're looking sort of, my population is, and I've got a very small university here. I've got 5 undergraduates at my university, but this is all the undergraduates at my university. And I want to calculate my variance and standard deviation. So here's my scores. 1, 2, 3, 4, 5 people. What I'm going to do to calculate my variance, I'm first going to calculate a deviation score. This is another principle that should be burned into your brain, somewhere on your body, tattooed deviation scores. It's going to be that important for you. And a deviation score is just taking our observed score and subtracting, in this case, the population mean. Okay? So here, 1, 9, 5, 8, and 7. I've got a mean value of 6. So if I take 1 minus 6, I get negative 5. 9 minus 6, 3. 5 minus 6, negative 1. So on and so forth. Okay. So I've got a vector of my scores. These are my observed scores. And then I've got a column of deviation scores here. Okay. Then what I'm going to do is I'm going to go through and I'm going to calculate the square of each of these deviation scores. So for each one of these, I'm just going to square it. It's going to give me a new column of scores, right? So 5 squared, 3 squared, negative 1 squared, 2 squared, 1 squared, have my squared deviation scores. And then what I'm going to do is I'm going to take these squared deviation scores and I'm going to add them all up, okay? This here is sigma. Don't be afraid of sigma. Sigma just means add up whatever is sort of listed after that, right? So we can see that to calculate this, we're just taking the sum of my squared deviation scores here, right? Natalie, why is it important for me to square these deviation scores before I go through and calculate my sum of squares?
So it could be a positive value.
There'll be a positive, and what happens if it's not a positive? What happens if I just add up these deviation scores?
You'll end up with like a skewed number. So it'd be like 3 minus 5. Minus 1, plus 2, plus 1.
Yeah. And what do I get if what am I always, what's my answer always going to be if I just add up those deviation scores?
0?
Yeah, it'll always be 0. By definition, mathematically, if you've done it correctly, if you add up all your deviation scores, it'll always get you to 0. And so that's not a helpful thing, right? So what we do is we go through and square those deviation scores, and then we add up and we sum up those square deviation scores, which gives us our sum of squares, okay? People who heard of sum of squares, give me a thumbs up if you've heard of sum of squares before. Some people? 1, 2. Okay, all right. Does anybody have a good intuitive sense of what sum of squares is? No, it's not a meaningful statistic in terms of something that I can tell you, right? If I was like, hey, Robert, so I've got this this sample, it's got a sum of squares of 40. Is that a lot or a little? Yeah, you don't know. It doesn't convey any meaning, right? But what you should know is that sum of squares are going to be super important, and the sum of squares is just a raw metric of variability. It's not scaled. So you can't interpret it. It doesn't have an intuitive interpretation. It's just a metric of variability, okay? And so when you hear sum of squares, know that this is just the sum of the squared deviation scores. Yeah. So what we're going to do is we're going to take our sum of squares, and what we're going to do is we're going to divide our sum of squares by the number of individuals in our population to get our population variance. Okay. And then what we're going to do is we're going to take the square root of that population variance to get the population standard deviation. And this population standard deviation is going to tell us, on average, if we draw a random individual from this population, on average, how far that person, any random score, is going to fall from the actual mean. Okay. So people kind of see how we went through and got calculated mean, our variance and standard deviation if we're working with a population, i.e. everybody of interest. Okay, so this is going to be how we go through and calculate sum of squares or how we calculate our variance and standard deviation for a population. This is kind of doing it by definition, but there are computational formulas for this that will go a little bit faster if you have summary statistics. Doing it this way or just plugging values into this formula, they're mathematically equivalent. They'll get you at the same spot. Okay. So what we always want to do when we go through and we calculate a score for variability, standard deviation, things along these lines, always want to take a look back at your data and say, is this reasonable? Any statistical operation that you do, you should always think to yourself, okay, here is an answer. Is this a reasonable answer? Okay, so I've got a mean in this population of scores of 6. Okay, I've got the closest value to this is 1 unit away. The farthest deviation from this is 5 units away. Riley, what does my standard what values of my standard what value does my standard deviation need to fall between?
I don't know. I'm confused on the question.
Okay, so can you tell me what remind me what standard deviation? How do we interpret standard deviation? What does this mean?
That's like approximately how far each score is from the mean.
Okay, so and we can literally interpret for the population. We can say the standard deviation is on average how far any randomly selected score is going to be from the mean. So if I calculate a standard deviation for this population, my estimate for standard deviation should probably fall somewhere between 1 and 5, right?
Mm-hmm.
Yeah, because otherwise, if I say, Allie, oh, my standard deviation is 10, why does that not make sense? Oh.
Hello.
Oh, there we go.
Okay, sorry. Can
If I showed you this graph, yeah. If I showed you this graph and I said, oh, I've calculated a standard deviation of 10, does that make sense given this graph?
No.
Why not?
Because there's not any point that's 10 scores away from...
Exactly, right? And so if it's actually anything even close to 1 or 5, I'm going to start to be question on whether or not. But if it's 10 or 7, that doesn't make sense. It can't be that because there's no individual score, much less many scores that are that far away, right? And so this starts to become important. If you have a good conceptual understanding of these statistics and what they mean and how to think about them, it's going to be an automatic check because you can get stuff and you can say, okay, does this make sense? Okay. And again, this Wilkinson paper, has anybody read Wilkinson yet? Give me a thumbs up if you read Wilkinson. Okay, Natalie's read Wilkinson. Robert said, okay, change your life, right? Like you're new people now having read this, right? Ton of good quotes. Rachel, you look skeptical, but like trust me, you'll get there. No substitution for common sense, or no substitute for common sense. Never assume a highly regarded program absolves you of the responsibility judging whether your results are plausible. Okay, like you always want to go through and say, does this make sense, right? Because otherwise, if you tell me that your standard deviation is 10, like this is what's going on in my head, I'm like looking at you, is like, does that make sense, right? Very skeptical, giving you side eye in my brain. Always want to go through and make sure that your that your results are reasonable. Okay. All right. So remember that. So this takes care of our population. But remember that the goal of our inferential statistics is to try and use samples to draw some conclusion about corresponding population parameters. Okay, and again, the whole process of our statistical models assumes that our samples are representative. Okay, what happens, Erica, if my sample isn't representative?
If the sample that you collect won't represent the population.
Yeah, exactly, right? So if you're wanting to look at, Erica, remind me what area of research that you're sort of working in?
Like goals and representation.
Goals and representations. Okay, so let's say like you're interested in goals of older adults, sort of later in life development or something like that. Let's pretend. And you go through and you calculate and you get a bunch of undergraduates and assess their goals. You'll get statistics. You can run analyses, but can we infer anything about the population of interest based on sort of what the sample that you've collected? No, we can't, right? And so what we need to assume is sort of everything that we do over the course of the next 2 semesters is assuming that the sample that we've collected is representative of a population of interest, right? Now, the problem comes when we're calculating variability is that we know mathematically that our samples consistently underestimate the variability in the corresponding population, okay? And the reason this is our extreme scores in a population, even if we have a nice normal distribution, my sample that I collect is very unlikely to get all possible people within that distribution, okay? So, Ariana, let's say, for instance, that you're interested in height of students at the University of Wyoming, okay? You've got a very exciting program of research that's looking at average height. If you go through and you collect a random sample and it's a random sample, right? It's sort of really every single student on every undergrad on campus is eligible to be involved in your study. You go through and you collect a sample of, say, 50 students, okay? And you measure all their height. Who are you likely to miss?
Probably just, I might be off this again, but like students that just like don't care to participate in research, like maybe the underachieving students or like just students who.
Okay. Yeah, probably, right? But let's say in this hypothetical example, they didn't have it. They didn't have the option. We just compelled them to come in and have their height measured for your study, and you get a sample of 50, and it's a true random sample, right? In terms of height, who are we most likely to miss or not be captured in your sample?
I'm sorry, I don't know.
What about people who are, say, 7 foot tall? Are we likely to capture them in the sample?
No, I guess so. Outliers.
Yeah. Well, what about people who are maybe under 5 foot tall? Are we likely to capture those people? Probably not, right? And these people are going to be extreme scores. They're going to be folks who are sort of existing out here towards the end of our distribution, right? And if we go through and we randomly sample folks, who are we most likely to capture? We're most likely to capture the people in the middle, right? And so when we go through and we're thinking about our samples, we can think about our samples as systematically, even when they're the best samples, even when they're random samples, we're going to miss those folks out on the end systematically. And if we're not getting those folks out on the end, Natalie, what's happening to our measure of the total variability in the population? Yeah, I'm underestimating it, right? Yep. Because everybody who's getting in my sample tends to be right here towards the middle. I sort of pick up some people now and again, but there's just not that many people out there, and I'm probably systematically missing them. And so the problem is is if we use the same approach to calculating variability as we do with our population, and we apply that to the sample, we start to run into problems, right? And so again, if this is my population variability, I've got everybody sort of going from the very biggest to the very smallest. But if I go through and I'm, Ariana, you continue to go through, and let's not say you grab one sample of 50, you go 2, 3, 4, 5, 10 samples of 50, you're going to catch on occasion some of those folks, but for the most part, you're going to get people out of that middle of that distribution. And when I'm calculating my sample variability, this in general is what the variability I'm capturing, when in fact this is the variability that I'm wanting to get. And so what we need to do is start to make some adjustments in how we're calculating variance in samples so that it's representative of the population that we're trying to represent. Okay. So what we start to become concerned about, and this will be something that we revisit again and again over the course of the semester, what we're talking about is biased statistics. Okay, so we will say a sample statistic is biased if the average value over an infinite number of replications systematically overestimates or underestimates the corresponding population parameter. Okay, so if I go through and in Ariana's study of university undergrads, and I'm looking for average height. If I capture 1, 2, 3, 4, 10, 100, 500 samples of 50 with replication, so going back through, and I take the average of all those measures of all those sample statistics, I'm going to have a value that doesn't represent the actual. It's going to underestimate the total population variability. And so what ends up happening is I end up with a biased statistic. Okay, we're going to say a sample, by contrast, a sample statistic is going to be unbiased if the average value of the statistic is equal to the population parameter. Okay, so Robert, let's talk about the mean. Okay, because calculating the mean of a sample and mean of the population, exact same process. Okay, where's the mean of this hypothetical distribution here? Yeah, right down here in the center. Where's the mean of this sample? Even if I capture 1 million different samples, where's the average of my mean of my samples?
It'd be right in the middle of that.
Right in the middle of this, right? And so we got the same thing, right? So when we're calculating mean is sample mean is an unbiased estimate of the population mean, because it doesn't matter if I'm looking at the population or the sample, it's all falling right down here in the same value, okay? But if I'm looking at variability, my variability of my sample ends up being somewhere between here. Variability of my population, much larger, so we need to make some adjustments in how we're calculating this. And so if we were to calculate our sample variance using our population formula, we'd end up with a biased statistic, okay? But the good news is, slight correction, we can change that the variance that we're calculating from our samples so that it's an unbiased estimate of our population parameter. Okay, so all we need to do is take that sample variance that we would calculate and divide it. Instead of, remember, in the population, we take our sum of squares, our sum of our squared deviations, divided by the number of individuals in the population. To make a correction so that we have an unbiased statistic, we still take our sum of squares. We just divide it by the number of people in our sample minus 1. Okay. Allie, if I divide my sum of squares by n minus 1 instead of n, what does that do to my sample variance? What's that? Oh, there we go. One more time.
Oh, sorry. It makes it less biased.
It makes it less biased? Yeah. What does it do to the magnitude of it?
Sorry, what was that?
If I take my sum of squares and I divide it by n minus 1 instead of n, what does this do to the magnitude of the size of my number here?
It makes it smaller.
Yeah.
Wait. No, it makes it larger.
Makes it larger, right? If I take a value and I divide it by one number, and then I take that same value and I divide it by that number minus 1, my results is going to go up, right? And what this does is by dividing by just using the same formula, but just dividing our sum of squares by n minus 1 instead of n, it's going to go through, it's going to reduce the denominator, make my denominator smaller. And if my denominator is smaller, what happens to my result? It goes up, okay? Another crucial thing, so statistics, like 80% of statistics is about ratios, right? And so be thinking about just basic mathematics. If I divide a number by a smaller number as opposed to a larger number, what happens to my result? It gets bigger, right? And so what ends up happening, all we need to do to make sure that our sample variance is representative of the population variance, we just, instead of dividing by the number of scores in our sample, we just divide it by the number of scores in our sample minus 1. That makes it a little bit bigger, and then we get an unbiased estimate. Okay, so if we're going back and say, let's this time, instead of a population of undergraduates at a very, very small university, we just say we have a very, very small sample of a population of undergraduates at a normal sized university, but our sample is 5, right? To calculate the variance and standard deviation for my sample, same thing, still going to go through calculated deviation score, still going to go through and square those deviation scores, still going to sum those deviation scores up, those square deviation scores up to get my sum of squares, okay? But now what I'm going to do is I'm going to take that sum of squares and I'm going to get my sample variance by taking that sum of squares and dividing by n minus 1 number of people that I have in my sample, okay? And again, Allie, dividing this by n minus 1 instead of the total number of people in my sample, what's that going to do to my variance, the value of my variance? We got you on a delay.
Okay.
There you go.
Okay. It makes it bigger.
I'm going to make it bigger. And why is this important? What was our concern with estimating sample variance in the first place?
It was underestimating it.
It was going to be too small. So what we're going to do is we're just going to divide our sum of squares by n minus 1. It's going to make that bigger. That's going to correct for that bias. Okay, and so what we end up with an unbiased statistic is that the average of an infinite number of replications of a sample of a certain size, if we take the average, all across those multiple replications, the average of my sample variances is going to be equal to the population variance, right? So it makes this an unbiased statistic. And then once we've got our sample variance, we just take our sample variance, take the square root of that to get our sample standard deviation, and we're good to go. Okay. So again, computational formula for sum of squares is the same, whether or not we're working with population scores, whether we're working with a sample of scores. Sum of squares is still the sum of the square deviations of your scores. We're just adjusting when we're calculating both the variance and then subsequently the standard deviation. Okay. So what we've got here is we've got, again, for this small example that we've done, we've got a population sum of squares of 40, sample sum of squares of 40. That's the same. That didn't change. But what we've got is we've got our population variance. If we're treating those set of 5 scores as everybody we care about, that's our entire population, we get a population variance of 8. If we treat those 5 scores as a sample of a larger population of interest, now all of a sudden that adjustment has increased our variance estimate to 10. Okay. Same thing with the standard deviation. If we're treating that as a population, we get a standard deviation of 2.83. If we're treating that as a sample, our estimate is increased because we're assuming that we're underestimating the actual variability in the population, so we make that adjustment. Okay. So here, these are just our formula here. And so, let me see, Brittany, where are we going to expect, so we've got this adjustment for correcting for bias in our calculation of our estimates of variability. Am I going to have more bias in small samples or big samples?
More bias in small samples or big samples?
Yeah.
I guess. I'm just gonna. Big ones? I don't know.
Okay. Where would we, if we're thinking about means, where would we find which do we expect more precise estimates in a small sample or a big sample?
Well, let me think of this logically. You want a bigger sample typically so you can be more reflective of your population. So a bigger one. Well, I don't know.
Nope. Keep going. Keep going.
Well, so what's the original thing you asked me again?
So am I going to expect more bias in estimate of my population in a small sample or a big sample? Which one of those is going to give me more bias?
Well, now that I thought, probably small.
Yeah, exactly.
Yeah, small, I thought through it.
Okay, good. And you're exactly right. Because conceptually, right, if I've got a big sample, right, as my sample starts to get larger and larger, let's say instead of a sample of 5, I've got a sample of 500, right? With a sample of 500, Riley, am I more or less likely to capture those folks at the end of the spectrum?
You'd be more likely.
I'm more likely to capture those. With my big sample, I'm more likely to get those people out on the extremes, right? And so with a large sample, do I need as much of a correction?
Still need.
Yeah.
No.
No.
Still need to correct, but I don't think you need as much.
Exactly, right? And so keeping with you, Riley, if I'm looking at this correction down here, this n-1, when am I going to get a bigger correction on this statistic? If I have a large sample or a small sample?
A bigger correction with a smaller sample.
Yeah, right? Because if I've got a sample of 10 and I'm dividing some number by 9 instead of 10, that's going to give me a pretty big difference, right? But if I'm taking this number and I'm dividing by 499 instead of 500, that's pretty small, right? And so what we see with this is an adaptive or a flexible adjustment. As my samples get larger and larger and larger, the need for correction starts to become essentially my sample standard deviation variance starts to become essentially this equal. It gets less and less bias as our samples start to increase, right? So with large samples, my correction is very small, but oftentimes we're working with small samples, samples of experimental groups of 10, 15, 20, something like that. And so the upward correction on this is going to be more noticeable. Okay. So people understand sort of what's going on with this correction and why conceptually it makes some sense.
I need to say this to make sure that I'm on the right track.
Yep.
So you do this so you're more reflective of your population, right?
Exactly.
Okay.
What you just said, Brittany, is the number one goal of anything that we do. Again, people get caught up with the weeds and the numbers and do I use SEM or HLM or something. Is your number one concern should always be we're not doing this to sort of learn something about our sample. We don't need to run statistics to learn something about our sample. We can just look at the sample, right? Sample's not the issue, dude. The issue is looking out at the population. We're wanting to infer something, to get some information about the parameters of a larger population. We can't observe it directly, but what we can do is get a sample. But what we want to do is make sure that the stuff that we're getting out of that sample tells us something about the population of interest. That sound good? Okay, cool. Let's take a break there. Let's take 10. Let's come back and be ready to rock and roll at 3:15. Cool. Okay, folks. What's up?
Your question, I'm so sorry.
Yeah.
What does the little funny looking U stand for?
The what?
The little U that looks kind of funny.
Oh, that's just Greek letter mu for mean.
Oh, okay.
Yep, that's just population mean. Yep.
Okay.
Yep.
I was making sure.
And so that just indicates that we're talking about a population parameter.
Okay. Thank you.
That's good. Yeah. Any other questions? Okay. Cool. How is this? Is this stuff ringing bells to folks? Is this sort of bringing back? Yeah. Okay. So not news, but just wanting to, again, as I said before, I can't emphasize how important it is to have just be really, really strong on these fundamentals so that we don't start to get lost as we sort of get down the road with stuff. So, perfect. You guys are champions. We're cruising along. Let's then go through and start talking about the utility of standard deviation. If you had any questions in your mind, you'd be like, why is he making such a big deal about standard deviation? When am I going to use standard deviation? Again, conceptually, right? Important to start thinking about this is our standard deviation is giving us it describes our distribution in terms of typical distance from the mean. Okay. It's just on average how far our score is falling from the center. Any distribution, some are going to be far away, some are going to be close, but our standard deviation is giving us, so again, roughly interpreted is on average how far scores are falling. Can anybody tell me why I'm saying like roughly on average? If I'm talking about the sample standard deviation? Is it the actual standard, or is it the actual average, or kind of an adjusted average? What do you think, Natalie?
I'm thinking adjusted.
Yeah. If I'm going to take an average of something, what do I divide an average or a sum by to get an average?
The N.
The n. Do we divide our sample statistics for variability by n?
It's N-1.
It's n-1, right? So in reasonably large samples, it's roughly the estimate. It's not specifically the estimate, but it's kind of, right? And so when I'm talking about this sample variance as roughly the average of the sum of the squared deviations from the mean, or the sample standard deviation as roughly the average distance of any given score from the mean, it's just because of that adjustment that we make there. So it's not technically that, but it's close enough for government work. Okay, so just wanted to make sure that we're clear on that. So if we, though, however, know both the mean and the standard deviation, it gives us some information about the overall distribution of scores. It gives us some information about if we were to randomly select scores from this distribution, where those are likely to show up. And it starts to give us a little bit more information on attaching meaningful interpretations to individual scores in terms of where they're at in a distribution. Okay. Does this graph look familiar? Okay. It's just our normal distribution, right? And if we see things falling on a normal distribution, this is a known distribution. Most of this class we'll spend talking about known distributions, because if we know what a distribution looks like, if we know what it's shaped like, we can start to attach probabilities of obtaining one score or another, right? So if we have a nice natural distribution, we know that about 68% of scores are going to fall within plus or minus a standard deviation, okay? If I've got a perfect, nice, normal distribution, about a little over 2/3 of my scores are going to fall within a standard deviation above and below. Okay. If I go through, and again, if I'm assuming a perfect normal curve, I'm going to have about 95% of scores falling above or below 2 standard deviations. Over 99% of my scores are going to fall within 3 standard deviations of the mean. Again, if I have a nice distribution. So if I'm working with something that I'm assuming has a normal distribution, and I know the mean, and I know the standard deviations, you can give me any score in that distribution, and I can start to have a reasonable idea of whether or not that's a likely score or a score that's probably pretty rare in whatever distribution I'm pulling. Okay, so let's say, for example, I've got a height of three guys, and I say the average height of men in the U.S. is 5'10" with a standard deviation of 3 inches. Okay, and I've got David comes in, and David's 5'6". How representative is David of? Is David short? Is David tall? What am I inferring about David?
David's relatively short. He's roughly between 1 and 2 standard deviations away.
Yeah. So David's a little over a standard deviation below the mean, so he's sort of outside of, that middle 2/3 of folks. So we'd probably say he's a little on the short side. Is he a weird case?
I wouldn't say so.
No. I mean, he's on the short side, but not something that would be unexpected. Okay. What about John, Robert?
Yeah, John is a little bit of a weird case in terms of what the mean is in the standard deviation.
Yeah. How many standard deviations above the mean is John?
But it's 3.1.
Yeah. He's over 2 standard deviations above the mean, right? And we know that 2 standard deviations above, we're starting to get up here, right? Matthew is 5'2", right? What's Matthew? Assuming Matthew is a human adult male in the U.S.
Matthew's also an extreme score. He's like 8 inches, so
Yeah.
2.6.
Yeah. So Matthew's down here, right? And so we can start to infer things about the representativeness of these individuals just based on the mean and standard deviation of our population. Okay, but this is kind of easy, right? This is easy because we have a general sense for what constitutes someone who's tall and what constitutes someone who's not so tall. If you say, hey, here's this dude, he's 6'6", you're like, yeah, that's a tall human, right? What about stuff that doesn't have intrinsic meaning? Okay, if I'm going through, and Rachel, let's say that I've got an extroversion scale, right? And I know that the mean in the population is 85 and a standard deviation, or let's say it's a sample. The mean of my sample is 85 and the standard deviation is 20, right? And I've got Bert here who has an extroversion score of 120. Is Bert extreme?
I don't know. It's hard to tell. He's about 2 standard deviations above.
Right, and so this is someone who's got a decent amount of extroversion, right? I mean, we know if we've got a score that's falling about 2 standard deviations from the mean, that's assuming we have a nice normal distribution. That's pretty high, right? What about Leon here? 125, just a little bit more, right? What about Reynolds? Where's this guy at?
Below.
Mm-hmm.
About 1.
Yeah. Little over 1 standard deviation,
Yeah.
right? So he's on the low side, but not too low, right? He's probably not someone who's sort of notable in that, like, oh, this is a strange case, right? And so we've got 2 different scenarios here. One, and this is something we want to be thinking about in terms of how we present statistics. In one case, we're working with a metric that has sort of known interpretive value. Like, we collectively understand, just because we've been around, what constitutes a large score, a small score, or something along those lines, right? But a lot of the times, particularly in psychology, we're working with made-up constructs, with made-up scales that don't necessarily have intrinsic meaning to them. And now all of a sudden, these estimates of mean and standard deviation start to become important. This is one of the things when I'm doing working on clinical team, right? And I'm reading a report and someone says, this person's score on social anxiety measure is a 56, right? Riley, does that mean anything to you? No. Doesn't mean anything to me either, because I don't know what this scale is or what it means, right? And so what I'll say is, hey, well, go through, please, and find some normative data to help me gauge whether or not sort of where this person falls, right? If we're talking about college students, so what's the average of the scale of just college students and standard deviation, so I can kind of get a sense for where this person is at, right? And then if I see that score is, 3 standard deviations above the mean on social anxiety, now I kind of know where this person falls on this scale, right? So we can use this to start to, and again, I can't emphasize this enough, we're not ever running numbers just to run numbers. We're running numbers to try and infer something about human behavior, and this is one way we can start to do that a little bit more efficiently. Okay. So, if we're thinking about standard deviation in inferential statistics, Okay, we're going to get into t-tests and regressions and ANOVAs and things along those lines. But what we're trying to do with these models is start to tease apart signal from noise. Okay, we're going to see differences, right? Ariana, you're looking at, remind me of what your research area is again?
Spatial cognition.
Spatial cognition. So let's say we're interested in, I'm just familiar with this because I've heard Meredith talk about it, differences in spatial cognition across gender differences across men and women, right? So let's say on average I find that my men in my sample are sort of X units higher in spatial cognition than the women, right? My goal is to try and sort of like, am I ever going to have a situation where my two samples are going to be exactly identical in terms of a score? Probably not, right? There's always going to be some difference, right? And what my goal is with our inferential statistics is to try to see, like, is this a difference that sort of constitutes or would be unlikely, assuming that these two samples came from populations with equal values? Or is this something that starts to exceed or look kind of different, right? So we're trying to carry out signal from noise. And if I'm working with data with low variability, it starts to become pretty easy to see where differences are happening, right? But as my data starts to get more and more variable, if we're thinking about variability as error, right? So here's my best guess for where this population falls, but there's a lot of variability into where people go. So my estimate of my mean as representative of my population has a lot of error in it because people jump all over the place. It starts to become harder to detect these differences and identify them as meaningful. Okay. So Erica, if I've got two experiments. I got experiment A and experiment B. In experiment A, I've group 1, group 2. Experiment B, I've got group A, group B. Which one of these experiments is it easier to see group level differences in? Just eyeballing the data.
Experiment A.
Yeah, why experiment A?
Because there's less variability within groups.
Exactly, right? So as Erica's looking at this, we're seeing group 1, everybody's sort of right around that 34, 35. Group 2, 39 to 41. There's not much variability in there, right? So whatever I'm doing, whatever my experimental manipulation was, is working pretty good. It's systematically getting people sort of pretty consistently on this. Okay, what's going on in experiment B, Erica?
There's a lot of variability within each group.
Yeah, here my manipulation might be doing something. There's a lot of static in there. There's just a lot of stuff going on. With experiment A, I can say, yeah, it looks like there's a pretty consistent difference there. In group B, it's really hard to sort of see any pattern with this, just because things are so variable. And if I go through and I graph this out, I can start to see this, right? Here, I've got my group A, or my group 1, my group 2. We've got the histogram, we've got the distributions here. It's very clear there's very little overlap between these two, right? We've got a difference of 5 points that's very clear to see, right? But if I go through and I take a look at my second experiment, I've still got a difference of 5 points. On average, my two groups are 5 points apart, but that same deviation, the same mean difference between these two groups, starts to become much, much more difficult to identify as something that's probably meaningful just because there's so much variability there, right? Here, my distributions are very separate from one another, right? In this other case, same mean difference. Only thing we changed is within group variability. Now it's very, very difficult to see whether or not we have anything meaningful or whether or not this is just noise in my data. Okay. And so as we start to move forward, particularly as we're thinking about our means-based statistics, right? Recognizing that we're not only interested in how much of a difference we're seeing between our means, we're also going to start to become very concerned with how much variability we're seeing within our groups, because that's what's going to start to contribute error and start to make it harder to see kind of what's going on with things. Okay. Questions about this? All right, cool. So just thinking about mathematics, some mathematical characteristics of standard deviation. I can add, subtract a constant from every score in a distribution. It's not going to change the standard deviation, right? If I have a sample of 100 scores and the standard deviation mean is 50, standard deviation is 10, right? And let's say I add 5 points to everybody in the distribution. Robert, what's my new mean going to be? It was 50. I have 5 points to everybody in the sample. What's my new mean of that sample?
You just had 5 points, so sorry, what did you say the original mean was?
50. Yep, my new mean is 55, right? It just changed it. So again, original distribution, standard deviation is 10. I add 5 points to everybody's score. What's my new standard deviation? 10. It doesn't change it, right? It just shifted everything around. It's not going to go through and change things, right? But if I go through and I multiply or divide each score by a constant, that's going to cause my standard deviation to change by that same constant, okay? So if I have, if I add 5, again, my original distribution has a mean of 50, standard deviation of 10. If I divide each score by 5, what's my new standard deviation? 2. Yep. And so just recognizing that as we go through and start to modify scores by a constant, the impact on standard deviation is a little bit different than what we see with the mean. Okay. When we're thinking about assessing and taking a look at our data and thinking about what types of things start to impact our variability, obviously our extreme scores. Okay, if we start to get values that are starting to be way out on the margins, this is going to impact our range. This is going to impact our variance, our standard deviation. All of these are going to start to become impacted by extreme values. Okay, sample size also going to increase. As my range increase, or as my sample size increases, my range is also going to increase, right? Riley, why does my range increase as my sample size increases?
Because this could be really stupid. I just feel like if you increase your sample size, you're just going to get more numbers that, like, it's highly unlikely that the numbers you get as you're increasing your sample size are only going to be within the maximum and the minimum.
Yeah.
So I feel like you're adding those.
Yeah, exactly. It's not stupid. You're right on point. Never apologize. Again, be unapologetically wrong. I'm calling on you for things that you don't want to answer anyway most of the time in this class. So, but you're exactly right. Thinking through this, if I get bigger samples, right, I'm more likely to capture those folks on the outsides. So as my sample size increases, my range is going to increase sort of proportionally, right? But what we see is our variance on our standard deviation stays pretty consistent, right? Because remember, in our small samples, I'm adding a correction to my estimate of my variance and my standard deviation. And in small samples, Rachel, what's the correction? Am I getting a bigger or a smaller correction with small samples?
A bigger correction.
A bigger correction, right? And so with a small sample, my variance is, or my standard deviation, let's say, is 10 because I've bumped it up a lot because I have a really small sample. As my sample gets bigger and bigger and bigger, I correct less and less and less for it, but my sample's capturing more of that variability, and so it stays pretty stable across samples, which is a really nice feature of our variance and our standard deviation. Range can jump around a lot across samples. So if I get sample 1, sample 2, sample 3 replications, right? Those of you in experimental stuff, we don't get beat across the forehead as much with replication demands in clinical, but for those of you doing experimental stuff, you'll want to. You'll notice that across replication samples, range is going to start to fluctuate quite a bit more than your variance and your standard deviation will. Brittany, why would we expect range to be less stable across replication samples than maybe our variance and our standard deviation?
Because with like different samples, you get each time you do like a new sample, and I think this is part of the reason why you do it. You get different people every time, so your range will be different. Like going back to what Riley was saying, like the different people you add, the more likely you are to get like the outliers and stuff.
Yeah, right. So it's a lot easier. Remember that my range is based on 2 scores, the min and the max, right? From sample to sample to sample, my min and my max might actually jump around quite a bit, right? But the average distance from the mean, that's going to probably stay pretty same. It's going to be less influenced by some of those out things, right? Now, the one thing where we run into a problem is we can't calculate range, variance, standard deviation, and open-ended questions. Remember, we talked about those censored data last time where we say number of miles driven in a week or in a month, 100 plus or something like that. I can't actually calculate a range statistic or a measure of variability with that, with those censored data, because we've said this amount, this amount, this amount, or over that. So we start to run into some problems there. So, and there's just different statistical models we have to use with that. We won't worry about that this semester, but know that they're there. Okay. All right. How are we feeling on variability? I'm going to do this because I want to see everybody feeling very excited about measures of variability. Yes, I like fist pumps. Like, I like it. Right? This is going to be, you're gonna, so many new tattoos in your first semester of graduate school on statistical modeling and things like that. It'll happen, or it won't. That's fine too. But all right, cool. So we're going to ship over and start talking about shapes of distributions. Okay. Again. Thinking about our nice normal distributions, this is what we always see in textbooks and things along those lines. In this situation, our mean, median, mode all going to be the same. Okay, so this is nice, but this is not how real data ever really look, right? We can also have different types of, so here's our symmetrical distribution. We can have different types of distributions that are still symmetrical, but just not normal. Okay, so here we've got a bimodal distribution, a multimodal distribution. It's still symmetrical, right? Ariana, why am I saying that this is still symmetrical?
Just spitballing, but because they're both like, I don't know how to describe this. Like, I don't know if this is right, but if you fold them in half, they'll be the same.
That's exactly what I was going to say. If you fold them in half, they're the same, right? They're the same thing on the right to the left, right? They're not normal, but they're symmetrical, right? In our bimodal distribution, we've got multiple modes. We've got 3 modes in the distribution B, but the mean and the median are still going to be the exact same, right? Now, in the bimodal distribution, are the mean and the median representative scores of the larger distribution, Erica?
Which one?
In the bimodal distribution, is the mean and the median a nice representative value for that overall distribution in the bimodal?
No.
Not really, because we really don't have too many people sort of there, right? And so wanting to think about, as you're looking at the shape of your data, does that measure of central tendency do a nice job of capturing sort of representative scores? In the multimodal, it might. In the bimodal, probably not. Would want to substitute sort of description of this with sort of identifying that it as a bimodal distribution and identifying the 2 modes. When we get distributions that are shaped like this, what's the first thing, again, that should be popping into our head in terms of a hypothesis?
Isn't it something about the population, like you sampled the population or something like that?
Yeah. Can someone expand on Riley's on the right track?
Likely to have like.
Oh, go ahead, Erica.
Is it like if there are like 2 different groups being collected?
Yeah, that's exactly what it is. When I see a bimodal distribution or a multimodal distribution like that, the first thing that comes to my mind, am I actually sampling 2 distinct populations? And probably you are, right? And so to wanting to think about what might be driving that distribution. Okay. We can also have, this is a different symmetrical distribution that's not normal. Robert, what's going on with this distribution?
essentially that you have the same mode across all numbers.
Yeah.
You have 4 of each number.
Yeah. What I've got here, we call this a square distribution, right? Like all values are the mode, right? The mean and the median is still reasonably representative, right? It's just there's no shape here, right? And so again, symmetrical. If we fold it in half, it's going to be good, but again, not normal. We can also have distributions that are not normal but not symmetrical. Okay, and this is where we start to get into a couple other statistics that help us describe the shape of distributions. The first one we would talk about here is skew. And in statistics literature, you'll hear this referred to as the third population moment. So your mean is your first population moment, your variance is your second population moment, skew is the third. Okay, and skew is going to give us an index of the symmetry of this distribution. Okay. So if I have a positive skew, and this is easy for people to get turned around. Think about when we're describing skew, positive, negative skew, we're talking about which direction the tail is going, right? So if I got a positive skew, tail is getting drug out towards higher values. Negative skew, tail is getting drug out towards lower values. Okay. And in these skewed distributions, we find that our mean is no longer a good index of central tendency. Okay, what's going to happen in a classically skewed distribution like this? The mean's going to get drug out towards the tail. Robert, why is that?
I'm sorry, you mind repeating the question?
Yeah. Oh, sorry about that. So we're saying that in a skewed distribution, mean is no longer maybe the best measure of central tendency. And what we see is the mean is going to be farthest out towards the tail in a skewed distribution. Why is that?
Because of like the outliers that you have, that essentially the modal data is showing that it's the other way.
Yeah. And so we don't even have to talk about it as outliers. I'm actually going to ask you to maybe scrub outliers as a term from your brain, just because it assumes a categorical thing where something's an outlier or not. But what we do have is extreme values starting to fall out, and they might not be outliers. They're just sort of values that are hanging out on that tail. And what that tail's doing is it's dragging that mean. Because remember, the mean includes all scores, but if we've got some scores that are way out here, even there if they're infrequent, it starts to drag that mean out, right? And so what we see is the mean getting dragged out towards the tail. The mode is going to be over here towards the hump, or the sort of most frequent or dense area of the distribution, and the median is going to fall right in the middle. So we'll see a lot of times with skewed distributions, people will start talking about using medians as a good index of kind of where that middle ground is. Okay. So this is skew. We also have kurtosis. Okay. Kurtosis is our fourth population moment, and kurtosis is an index that starts to give us or describe information about the shoulders or the peak of a distribution. Okay. So if I've got positive kurtosis, sort of the technical term for this is leptokurtic. This is going to be a distribution with a pretty narrow peak and heavy flat tails that go out, right? The tails kind of flatten out here, but we've got everything kind of stacked up and got a peak, right? Negative kurtosis, this is the opposite. Here we don't have much tails at all. We've just kind of got this moundy kind of sort of rounded hill type of distribution. So no real tails, kind of a flat peak, flat center, and sort of these really heavy shoulders. Okay. What we see is our kurtotic distributions tend to underestimate our population variance. Doesn't matter if it's negative kurtosis, doesn't matter if it's positive kurtosis. Kurtosis in general underestimates the population variance. Here, we've got tails coming out, right? And we're like, okay, well, those are sort of getting more representation out in the ends. Brittany, where are we missing scores in our positive kurtosis?
Well, since you it looks like you have a, maybe on the shoulder part
Yeah.
is where you're missing.
Exactly. Right here, right? These places, all this point where we should have data, we don't, right? And so what we end up doing is with our positive kurtosis, we're still underestimating variability, right? Because everything's kind of stacked up here in the middle. Negative kurtosis is a little bit easier to see, right? Because we're not getting any of those tails. So kurtosis in general tends to underestimate our population variance, right? So if we got kurtotic data and we're assuming that our population should be relatively normal, kurtosis starts to impact or underestimate our variance. Okay, and this can impact our equality of variance tests, and it can bias both our parameter estimates, our standard errors. We'll talk about why that's a problem sort of as we get down the road. So this would be this is an example of a kurtotic distribution. Okay, it's square. There's no peak. There's no tails. It's just kind of very square. So this would be again an example. Positive kurtosis is kind of easy to think about. It's just kind of thin at the top and then kind of flattens out. Here we've just got a square. This would be an example of negative kurtosis on this distribution. All right. So when we're talking about indices of skew and kurtosis, these are numbers, and depending on what program you're talking about. So skew in a normal distribution has 0 skew. Technically, mathematically, kurtosis in a normal curve has a value of 3. And so for Robert and Allie, when I'm having you use data, you'll see neutral kurtosis is given as a value of 3. Everybody else in SPSS, SPSS just subtracts 3 from the kurtosis value to make sort of neutral kurtosis equal to 0, right? But what we have is we have sort of these metrics, sort of measuring skew and kurtosis as a number. And what we have tests that will test for whether or not you have significant kurtosis. But the problem is with these tests, and we'll talk about this in a while, you never want to use these. If you see someone reporting significant tests for skew and kurtosis, that's not a helpful thing to do, okay? Because if our samples are large enough, anything that deviates sort of even a little bit from 0 is going to come up as significant. Statistical significance, anything that's significant just means it's likely not 0, right? And we don't assume, an assumption of our statistical models isn't that our data is perfectly normal. So we want to start thinking about this as when we're gauging non-normality, we want to not focus on statistical tests. What we want to start doing is looking at the actual values of our skew and kurtosis, and sort of looking at the distributions and start trying to describe it from there. So in general, in psychology, if you've got skew and kurtosis values less than 2, again, assuming 0 is representative of neutral skew and kurtosis, we say we don't call them normal distributions. We're just going to say that it's probably not bad enough to be too concerned about, okay? So again, we're not saying, it's not non-normal. We're just saying that as long as our skew and kurtosis is generally around that, we could probably say, yeah, it's not something we're going to get too worked up about, okay? But always remember that these violations exist on a continuum. We don't have non-normal data and normal data. It sort of exists somewhere in between this, okay? You'll start to see, depending on what type of analysis that you're running, skew less than 2, kurtosis less than 8, interpreted as non-problem, but you need really big samples for this, and it starts to become hard to get that type of guidelines past reviewers. I've done it. But it's definitely, those start to get into large values, okay? And the thing to remember is that our impact of non-normality, as our samples get larger and larger, and we'll talk about why this is, we start to become less and less concerned in many cases about sort of where our skew and kurtosis values. If they're insane, then yeah, it's still an issue. But if we've got concerns with kurtosis, and this is just from Tabachik and Fidel. If I've got a sample of over 100, I start to become less concerned about positive kurtosis. Negative kurtosis starts to become negligible at sort of samples of over 200. So unless it's really, really extreme, and we would still note that it's really extreme, the question is this something that causes a problem for my analyses? So wanting to think about it from that perspective. But always, and this is, again, a thing across everything that we do in this sample, you should never be using bright lines, right? To say, oh, my data has a skew of 1.95, and so it's fine. And Erica's data has a skew value of 2.05, and so it's completely terrible, right? If I've got a skew of 1.95, that's a pretty skewed data set, right? It's not 2, but it's not great, right? So as we go through, and this is hard, right? Particularly in statistics, we want to think about things in terms of rules and sort of if then that type of things, which we'll do a little bit. But what we don't want to do is sort of say, oh, if it's above this level, then it's fine. If it's below this level, it's fine. You want to be thinking about everything that we do this semester and next semester. Well, you're not going to have me next semester, but as you go on, work with other people, thinking about this as a continuum. Okay. Questions about this?
What does, I understand skew, which kind of says that like a lot of your data is at one end, right?
Mm-hmm.
But like, what is kurtosis? Like, if this happens, what is it telling you that like? Is that an accurate question? Like,
Yeah, no. I think that's a great question, Brittany. It's harder to kind of put into sort of words and say, oh, okay, this is. It just means that everybody's kind of either clumped up and kind of in the center and sort of with not a whole lot of stuff on the tails. Or if it's positive kurtosis, it means everybody's very peaked, like sort of most everybody's right here in the center, and then it starts to get narrowed down, and then we kind of sort of flatten it out. So it's just giving you a sense for a violation of normality or how things are not sort of conforming to a nice normal curve.
So it's like if you see this, you know, like, oh, something's wrong. It's like
Well, not necessarily.
Not necessarily, but like, you know, given all these guidelines, like something may be up.
Yeah, and I might think about that. And so, but the other thing too is it starts to become important to start thinking about what am I measuring? How big is my sample, right? If I've got a sample of 20, samples of 20 are never normal. They're always sort of wonky and look weird and stuff like that, right? And so as we move through and we start to look at data, like this is a thing, like I can describe to you kind of what it's like, but there's a lot of it is just seeing data sets and saying, okay, that's weird or that's not typical type of thing. But your head's in the right place and wanting to understand sort of this. Kurtosis is just kind of telling you, does this deviate from that nice normal bell curve?
Can I ask a question?
Yeah.
It seems like kurtosis has a lot of limitations, and like at least what the previous slide kind of said. So like, and then kind of the theme of like the paper that we read in terms of doing things parsimoniously, like as simple as possible. But I'm just like kind of confused as to what kurtosis could even further prove if it's just a benchmark. Yeah. I don't know. It seems. Yeah.
I think, and that's. I think your head's in the right spot, Robert. Think about this as just a way, as a mechanism to describe the shape of data to other people. Okay. And so if I'm looking at a distribution of scores and I'm saying, and an assumption of my test is that my data should be relatively normal, right? The kurtosis is just kind of giving me a sense for what this shape looks like and how severe it is. Sometimes we'll find stuff that's like, oh, that's pretty terrible, but a lot of our means-based statistics are pretty robust as long as we have reasonable sample sizes to a lot of this stuff, right? And so it's just a feature of the data that's helpful in describing to other people or justifying certain types of of analyses to say, okay, this is kind of what it looks like. These are the decisions I made because of this. So it's just a nice way of summarizing aspects of your distribution.
Almost exclusively then reserved for very large samples.
Well, I mean, we'll go through and we'll calculate kurtosis on big samples, small samples. The issue is just knowing sort of the context, right? And so if I've got a small sample of like say 15, but I've got a kurtosis of 3, right? And I'm like, well, it's because I've got a small sample. I'm probably not super concerned about that. If I've got a sample of like 300 and I have a kurtosis of 3, that tells me something different in a sample of that size than it would in a sample of smaller size. Okay, and we'll go through and we'll talk about in screening. You'll have lots of opportunities to look at different types of data and start to get comfortable using some of these terms to describe data. Sound good? Cool.
I also have a question.
Yes.
But it's not specifically about kurtosis. You might have explained it and it might just gone right over my head. But when you're talking about like the mean is first population, variance second population, kurtosis fourth population, what does that mean?
Yeah. So one of the things I want you to do and hope that you all get out of this is being comfortable reading methods literature, because a lot of times it's intimidating, right? I go into I've got an analysis that I want to do, or the analysis that I want to do I can't do because of some feature in my data, and there's an alternative, but I need to go through and sort of learn something about that. In statistical literature, you'll see this used to identify or talk about different aspects of the shape of distributions. And so your mean, and they talk about these in terms of moments, right? So think about these. You can think about these as just different characteristics or descriptors of your data. You can think about it as the big 4 personality factors of a descriptor, right? You got your first one is your mean. It's where the middle is, right? And then your second one's your variance, how spread out things are. And then your third one is your skew, how skewed things or symmetrical are things. And then your fourth is sort of the shoulders of the distribution, or are they humped, or are they not? And so in the statistical literature, for your purposes, this is more along the lines of just random bar trivia stuff. But what I want to do is present this. So if you are reading, say, Natalie, a methods paper, sort of a couple years down the road, and then you see someone talking about the second population moment, you know that I go, they're just talking about the variability of the set. Does that help? Cool. All right, other questions about this? All right. Oh, that's me giving you side eye. If you're using bright line benchmarks, that's what's going on in my head. So don't say, oh, it's just this, so it's fine, or it's not, so it's not. Just, again, wanting to think about things flexibly. This is, if you're interested in the skew and kurtosis formula, this is a half formulated thing. You don't have to worry about that. Okay, cool. Let's stop there. Take another 10-minute break. Come back at 4:10, and we'll finish up with this, talking about some extreme values and stuff like that. Cool. All right, folks, how are we feeling? You ready for the final stretch? Okay, nice. Any questions about anything we've covered up to this point? Feeling comfortable, like, again, trying to kind of, some of this stuff kind of coming back to you in terms of basic principles and things? Okay, cool. So, gonna start in, I think I actually tweaked this slide a little bit in terms of talking about adding not just outliers, adding extreme values to this. Outliers is a tricky. Outliers is a tricky thing. Outliers implies that there's some consistent definition of an outlying value. This is an outlier. This isn't. If it falls on this line, it's an outlier. If it falls on the other side, it's not an outlier. What I'm going to do is encourage you, and throughout the semester, is to be thinking about these as extreme values. Okay, extreme values, I think, captures the idea that we can get increasingly extreme, and as we get increasingly extreme, it starts to become increasingly sort of potentially unique or interesting data. But again, I'm going to do my absolute level best over the course of the semester to push you off of thinking about sort of these categorical, this is this box, that's box, thinking about things in terms of continuums. Now, if we're talking about a univariate outlier or extreme value, this is going to be an extreme case on a given variable. Okay, and anytime in a data set, if we see extreme values, we never want to just say like, oh, that's an extreme value or that's an outlier. Okay, anytime you see an unusual score, you should be thinking in your head, how do I understand this? What's going on? Because there are a number of different possibilities. One, that data point could be just an incorrect data entry. Show of hands, people who worked in undergraduate labs. Yeah, probably pretty much everybody or close to everybody. Did you ever enter something wrong in a data set? Probably, just because it's something that happens, right? With manual entry and things like that, there's all sorts of opportunities for a score to have an extra 0 added to it or something along those lines. So probably number one cause of extreme values is going to be incorrect data entry. Okay. Another thing you will see in SPSS, there are certain numbers that you can enter that indicate to SPSS that it's a missing data code. 999 is one that I use a lot, right? And 999 means that someone skipped this question. Because if you just have missing data in your data set, and I'm going through and I'm taking a look at it and I just see missing values, I don't know if that's missing because someone forgot to enter it or if it's actually missing or what happened. But if I see 999 in there, I know that Allie was coding a questionnaire and this person literally skipped this question, and that 999 is a placeholder saying, yep, this data is for sure missing. And then we can tell SPSS, hey, treat 999 as a missing value. But if we forget to tell SPSS that, then 999 is going to be an actual real number. And so wanting to make sure that you don't sort of get turned around there. Another thing that can happen is what we might find is that a case is not, extreme value isn't actually a member of the population that we want to study. Okay, so let's say I'm interested in income of college freshmen. Okay, because I'm interested in sort of socioeconomic stressors and university freshmen, something like that. And so most people are coming in with little to no money, but then let's say I have someone making like 6 figures or something like that. I take a look at that person, and this is a 45-year-old professional who's coming back for some sort of continuing education or something like that. That's probably not a person who I'm interested in sort of being in my sample, so I can go ahead and get rid of that person, right? Other thing that can happen is this is a case that is a member of the intended population, but it's just the variability that I'm able to capture in my sample is just underestimated because I've got a relatively small sample. So let's say that I'm interested in, let's say, cocaine use among college students, right? I don't think anybody here is doing active substance use research, but what would we expect the distribution of, let's say, monthly use of cocaine to look like in undergraduates at the University of Wyoming? What's going to be the shape of that distribution? Is it going to be normal? What do you think, Allie? You're saying no. There we go. It's not going to be normal. Why isn't it going to be normal?
Because, I mean, I don't think most people are using cocaine on a regular basis.
Right. And so it's probably not going to be, it's going to be super skewed, right? But I might get somebody who reports, let's say, use 6 or 8 times a month. I'm not a drug person, but that seems like a lot for a university undergraduate. And I've captured that person. Do I want to throw that person out? Not necessarily, because that's actually who I'm probably wanting to make sure that I'm getting people who have high levels of use, right? And so what I need to do is then go through and check. I'm like, nope, it looks like this is someone who's a heavy user that I want in my sample, but I just need to figure out how to deal with this now. I don't want to throw them out because then I'm systematically throwing out the people I'm actually interested in looking at, but just want to take it from there. Okay. Now, the thing that can happen in terms of consequences if we don't do anything with these data, it can start to have these individual values or sets of values can start to have an inordinate influence on our different estimates and our different coefficients, which isn't good. We can it can throw our type 1 and type 2 error rates off, which we'll talk about down the road, and it starts to reduce the generalizability of our solution. Our data look different in this sample because of one or two people than they would likely look in other samples that I would collect. And so for all of these reasons, we want to be at least mindful of extreme values in our data. Okay. The good news that I can tell you, having sort of worked with psychological data for a while, the nature of what we do reduces the extent to which we often will need to worry about outliers relative to some other areas. Okay. A lot of times we're using self-report measures or different interview scales or things along those lines. And so there's a limit, like you can be high, but there's a limit to how high you can be, right? You can't get way out of bounds. But if I'm, say, an economist and I'm looking at home prices or income or things along those lines, we can get outliers that are or extreme values that are very orders of magnitude larger than the rest of the other things that we're studying. And so that's where this really starts to come into play. So we've got less of an issue in our in psychological data, but it's also always something that we want to go through and take a look at and make sure that we're being mindful of and addressing them when they do come up. Okay. One thing that you want to be thinking about is recognizing is that you can have extreme values or outliers within categorical data. Okay. Let's say I'm looking at demographic variables where I've got looking at men and women, or a proportion of individuals identifying as racial ethnic minorities in my sample. If I start to get splits that start to exceed like 9-to-1, what we find is those in cases in those in the smaller set, in the smaller group, have a great deal of more influence than those individuals in the larger category. Think about this as sort of political power in the Senate in Wyoming, right? We've got like 500,000 people in the state, and we still get 2 senators, whereas California has 1 billion people, they get 2 senators. Sort of me, as a resident of Wyoming, sort of proportionally, conceptually have much more of an impact on sort of things in Washington than any individual in California. Same type of thing with these dichotomous variables. If I've got 10 women in my study and 90 men, any one of those women start to have a much more larger influence on that group than any one of the men do. And so that starts to become problematic. What we can see with these extreme splits, it starts to make our correlations with other variables smaller. We also start to get weird, spurious associations that probably don't generalize to anything. And so when we're thinking about screening our data, we not only want to be looking for extreme values in our continuous scores, but we also want to be looking at our dichotomous variables or our categorical variables to make sure that we've got reasonable, and it can be pretty far off. Again, 9-to-1 split is pretty intense, right? But recognizing that we start to have problems, and what we need to do is, unless this is a variable that's crucial to our analyses, maybe we leave this one out. Okay. Questions on this?
This is just kind of like a question that, so, I'm looking at this ethnicity one, right? And
Yeah.
it's white 304, and then like any other ethnic minority is 22, which we find a lot, like read articles and stuff.
Mm-hmm.
So, like, this is just me wanting to know, like, what do you do? Because obviously you don't get rid of those people. So, do they have more influence? You know what I mean? So, like, if you're doing this ethnicity right here, these numbers, if I'm correct, they're more reflective of, like, what white, non-Hispanic thinks than anyone else, right?
Yep, exactly. And that's the thing, right? Like, if I wanted to look at, and so these are data from a research clinic in Buffalo, New York, right? And so Buffalo, New York, at least the folks who were coming in with us were predominantly identified as white, non-Hispanic, right? Now, And so my sample and thinking about the population, this study is representative of white majority culture in Western New York, right? Individuals of color are not well represented in this, and so that's a huge limitation of these data, right? Where I start to become, and it's not optimal, but if I'm recognizing that and sort of make that very explicit, that sort of at least says, hey, this is the limitation of our data and who we can speak to with these analyses, and it might not generalize to another group. But where I start to run into problems, if I want to start looking at, and obviously I don't need to tell you all this, collapsing everybody who's not white, non-Hispanic into the same group is a terrible way to do things, right? And so one, that would be an awful way to go through and try and tease things apart anyway. Two, from a statistical standpoint, I just don't have enough representation in here to make this a good variable to include in my model. And if I try, there's a good chance I'm going to get weird, funky stuff that may not be representative of sort of group level differences here. And so there's just a lot of problems with this. And so in that case, I wouldn't exclude these individuals from my set by any means. I sort of want to keep them. They're still sort of data. And differences in background may or may not impact the thing I'm looking at. I don't know, right? But what I would need to be very careful in doing in both of these cases is saying, oh, I want to look at gender differences in this, because I just don't have enough men in the sample to do that, right? So wanting to be careful with this. Yeah. Does that help?
Yeah.
Okay. All right. With extreme values, again, you'll often see extreme values, and we'll do this. We'll operationalize extreme values as scores exceeding some z-score in our sample. For large samples, you'll see 3.29. That corresponds to a p-value 0.001. And so this is a nice way to just indicate and communicate how far out these scores are. But again, what we don't want to do is say, oh, because this is a value, this score has a z-score of 3.28, and so it's fine. And this one has a value of 3.30, and it's an outlier. Those two scores are the same. Functionally, they're the same thing, right? We can use these benchmarks to try and sort of qualify the extent to which these values are extremely unique within our set, but we don't ever want to use bright lines. Other thing, too, is we always want to provide some sort of graphical representation, because then if Allie says, oh, hey, I have an extreme score that's 3.29, I don't know, right? That extreme score might just be a continuous portion of the distribution. It's just kind of got a skewed tail. So, I mean, yeah, it's extreme, but it's not any more extreme than the 7 scores that are right next to it, just on the other side of the line, right? That's a different thing than if Allie says I've got a z-score of 3.3 and it's an extreme value where I have everybody else hanging out over here and I got 1 or 2 cases out here. That's a completely different situation, right? And so these graphical representations are going to be important. And then recognizing that when we have very large, as we start to get larger and larger samples, I'm almost always, if I don't have extreme scores, if I've got samples of 200-300, and if I don't have large scores that are hanging out there on the ends, that's kind of a weird thing, right? The whole idea is our samples get larger and larger, we're going to be picking up those folks on the outside, right? So just because you have extreme scores doesn't mean that your data is bad or they're weird or anything like that. We just want to identify them and then follow up, make sure that we understand who those people are and what they're doing and whether or not those are real scores. Okay. Does that make some sense to folks? Cool. All right. So when we're thinking about graphical distributions, I think we don't do enough in our literature, and particularly in sort of these types of classes, of utilizing graphical representations to communicate things very efficiently. Okay. One way we can go through and do this, bar graphs, right? You all know bar graphs. Bar graphs are easy peasy. Here we've got racial ethnic identification of a sample, right? We're seeing that we're majority of the preponderance of individuals are identifying as sort of white non-Hispanic here. We've got individuals, a good number of individuals identifying as African American, and then sort of very minor representation of participants identifying as Hispanic or Native American, right? I can put those in numbers, but it's really easy to see this in a graph. It just makes it pop. It communicates it lots lots easier. Also, if I'm looking at mean-based analyses data going on, Rachel, what can you tell me is going on in this graph right here?
So there's a lot more amusement. Sorry, I'm trying to read it.
Yeah.
In the humor film versus the sorrow film.
Mm-hmm.
But then when you look at the breakdown of, I guess, the two bars,
Mm-hmm.
I'm not sure what that represents. So
Yep.
trauma versus no trauma.
Yeah. Doesn't matter. You're doing a great job. Yeah. Yeah. And so what are you seeing right there?
Well, there's a lot of overlap in terms of the error,
Mm-hmm.
but one of the graphs or one of the groups has less humor for the amusement or the humor film versus the other group.
Yeah. Right. So what that did is that graph with zero. No, you did an amazing job with no information about this study or anything that we did here. Like you were able to pull a lot of information and start to make some really rough interpretations about what's going on, right? And here, with a little bit more information about sort of what we did and what we measured and what these error bars correspond to, you can start to make some pretty subtle and intuitive and important inferences from this graph. And it's an easier way to do it than sort of try and go through and describe to you, because you can just look at it and see, right? So again, always, if you're trying to figure out how do I present this, always remember that graphical representations are a nice way to go through and do this. In terms of describing distributions, histograms are really, really nice. If we've got frequency distributions of continuous data, we can go through and very quickly, and I can give you mean, median, mode, standard deviation, skew, and kurtosis. But if you just give it to me in a figure, it's much easier to see that and sort of exactly what's going on with these data, right? Erica, what are you seeing in this CAPS total panel right here?
It is skewed negatively.
Yeah, yeah.
Yeah.
Okay. How would you describe the shape of this distribution?
I don't know.
Yeah, I might call this normal-ish. The one thing with histograms is depending on how you bend those categories, it can start making that histogram look a lot different, right? But here we've got a little bit of skew, negative 0.3, negative 0.4. That's not too bad in terms of the negative skew. My negative kurtosis, this is telling me that I've got kind of a boxy distribution. I don't have tails that come out. It's kind of sort of boxy here, but I can start to go through and kind of see. Erica, is my mean value of 79, is that a reasonably representative value for this set? Yeah, ish, right? I mean, so my, I've got, looks like a minimum of 40, a maximum of, let's say, 110. So I've got a range of 70-ish. Standard deviation of about 17. So scores are pretty spread out, but I don't have anything too wild going on here, right? Riley, what about this second panel here? How would you describe these data?
Well, I would say that this one is definitely skewed positively.
Uh-huh.
And their kurtosis value being positive, it doesn't have the shoulders.
Yeah. Yeah. So you're right. So here we've got a skew above 2. So we can see this is quite skewed, right? And our kurtosis value is quite large, right? So it's saying that we're pretty peaked and sort of you got these flat tails that come out, right? So again, is my mean value of 0.5, is that a good representative number for this distribution?
I would say no.
Yeah, I mean, a mean value 0.5 isn't a real value that you can have, right? Well, you don't know this, but I do. This is like sort of 1, 2, 3, 4, 5, right? Is not terrible. But again, because my scale is pretty truncated, but again, sort of my representative value is sort of my median, my mode 0. Like most people are reporting no anger in response to this film, right? So again, using this histogram supplemented with some of our statistics to try and draw inferences from some of this stuff. Okay. Last thing we're going to talk about is box plots. Okay, I'd given you a heads up about box plots, told you box plots were coming. With our box plot, we've got sort of these sort of folks right here. And what's nice about the box plot is with my frequency dish or with my histograms, depending on how I bend the data, can make that graph look very, very, very different. The decisions I make are going to change the shape of that graph. With box plots, different features correspond to different aspects of the data, and so there's not much I can fool around with this. Okay, so with box plots, that midline right here that I've got circled in this, this is going to be your median. Okay, Robert, tell me what the median is again.
Middle value. If you were an even, or if you have an even number, you would either take one or the other, and then odd value would take the one in the middle.
Yep. Yep. So this midline is my median, not the mean. It's the median. Half of the scores in the distribution fall above this line. Half of the scores in the distribution fall below it. Okay. Robert, you're on a roll. I'm going to stick with you, man. The bounds of the box. Okay. So this piece here and this piece here. This corresponds to your first quartile and your third quartile. Robert, remind me what your first and your third quartile are.
That'll be the 25th and the 75th percentiles.
Exactly, right? So we know that 25% of the scores fall below this line, 25% of the scores in the distribution fall above this line, okay? And the middle part here, this is my interquartile range. The bounds of the box cover your interquartile range. This is your middle 50. This is 50%, half of your scores fall between this line and between this line, okay? Then we've got your whiskers. This is your inner fence, okay? Now your whiskers can correspond to a couple of different things. Your whiskers can correspond to the minimum and maximum values, okay? And so if you look at sort of these whiskers here, this is the max, this is the min, that's the max, the min, okay? But in cases where you have some values that are some extreme values that are falling beyond 1.5 times the interquartile range. So if I take this interquartile range and I take 1.5 times that from sort of the first of the third quartile, the bounds of the box are going to correspond to the most extreme values that are still within 1.5 times the interquartile range. And then any extreme values, these are going to be indicated as individual points, asterisks, or open circles that extend beyond the whiskers. So in SPSS, you're going to values that are falling greater than 3 times the interquartile range are going to be indicated with an asterisk. In Stata, they're just all sort of the same indicator. But any points that you would see beyond those whiskers are going to be values that are extended beyond 1.5 times the interquartile range demonstrated here. Okay. And so if you've got data that have a relatively normal distribution, about 95% of your scores should fall between your two whiskers. So someone, Allie, tell me what are you seeing in this graph right here?
Can you hear me?
Yep, there we go.
So it looks like in conditions like one and two about the same ish. 3 is also similar, and then 4 has 2 like outliers that aren't included in the.
Yeah. And so, Allie, for conditions 1, 2, and 3, what does the top of the whisker indicate?
That the max
Yep.
values are about the same.
Yep. And here we're seeing sort of the minimum, right? And so here for these first 3, we're seeing that the median value, the distribution for conditions 1 and 2 are about identical, right? So we've got functionally identical medians. Interquartile range is about the same, maybe a little bit bigger, but not anything to speak of. Min and max is about the same. So I would say that conditions 1 or 2 are functionally identical. What's going on, Natalie, with condition 3 relative to 1 and 2?
Condition 3 has a slightly wider range, if I'm looking at it right, and the median is slightly higher.
Yeah, little bit higher median. I don't know if I would make too much about that, but you're exactly right. It's a little bit higher. Interquartile range is a little bit wider. So we got a case that's some data that's a little more spread out. The minimum value is quite a bit lower here, right? And then, Erica, what about condition 4 relative to conditions 1 and 2, let's say?
Condition 4 also has a larger spread, and then it also has outliers or extraneous.
Yeah, some extreme values there, right?
Extreme values.
Yeah. So if I'm looking at the median value, how's my median compared to conditions 1 and 2?
The median seems like the same.
Yeah, it's about the same, right? But what I'm seeing in condition 4 is it looks like maybe a little bit more spread, not around the middle 50. My interquartile range is about the same as what we've got here, but there's something going on that's creating more error, right? I'm getting more variability in this group relative to some of the other 2, right? So just looking at this, I can start to say, well, am I going to have median level differences, or is the center value different across these conditions? I don't know. They look kind of the same. Whatever I'm doing in these experimental conditions is starting to impact sort of how far people are going. Here, getting pretty consistent responses. Here, I'm starting to get more variable responses, right? So these are the types of things you want to go through and start to attach information from, right? It's easy to go through and say, here's the median, here's the first quartile, here's the third quartile, here's min, max, here's values that are extending beyond 3.5 or 1.5 times the interquartile range. What you want to do is start attaching sort of some type of meaning interpretation to these data. Okay. What about, Aaron, what's going on with this graph here?
It looks just like the whole graph in general.
Yeah. Just what are you seeing going on in this graph?
So the medians are relatively the same in conditions 1, 3, and 4, and it's a little higher in condition 2.
Mm-hmm.
And the interquartile range is pretty similar as well, but there's a lot of variance, especially in condition 2.
Yeah. What about, Aaron, how would you describe the shape of these distributions? We don't have a histogram, but if you looked at a histogram, what would that histogram likely look like?
I would say it has more of the negative. Wait.
Yeah. Yeah.
Yeah.
Okay. So what we've got here is, this is from my dissertation. I was doing some physiological stuff and just wanted to make sure, because I'd taken heart rate and heart rate variability and stuff like that. Wanted to measure it, see how much people were exercising, right? And so this is weekly hours of exercise, right? And so what's my Ariana? I'll keep it with you here. What's the min across all of these conditions?
0.
0. Everybody's the same. Everybody's 0, right? But across each condition, I'm starting to capture here. I've got a skewed distribution where most people are probably somewhere around 0 to 5 hours a week, right? But I've got some individuals in each one of these conditions who are reporting fairly high levels of exercise, right? And so what we're starting to see here in SPSS in condition 1, case number 42, 23, and 12, these are all values that are falling. This is the value that is the most extreme value that's still within 1.5 times the interquartile range. But we've got cases 12, 23, and 42 that are falling beyond 1.5 times the interquartile range. Then we got case 8 and 70 that are more than 3 times the interquartile range, right? Same thing here. This is the value that's the most extreme value in condition 2 that's still within 1.5 times the interquartile range. And then we got 38, 20 that are beyond 1.5 times. 71 is beyond 3 times the interquartile range, right? And so if I'm looking at this, I'm thinking that, boy, 20 hours a week in terms of exercise, that's a lot, right? But who might I be capturing if this is a university sample?
Maybe like D1 athletes.
Yeah. This was at the University of Memphis, right? And so I've got athletes, right, who are probably in practice and things along those lines. Probably is my guess. We could have people who are just fitness fanatics, or people who maybe have some eating pathology or some stuff going on here, right? But what we can do is start to infer quite a bit out of this graph. Okay. So thinking about this, again, we're going to go through this back time and time again, but I think some words to live by out of your HAL text, not to think about any of this as cut and dried facts, okay? What we're going to do is we're going to take information, we're going to sort of look at it, we're going to take it within context and try and attach some interpretations to it, right? Remembering that we can't separate statistics and our experimental design. I can't control for the fact that you ran a terrible study, right? There's not a variable that I can go through and use with statistical magic to go through and do that, right? So we need to be thinking about the design, what variables we're getting, sort of the extent to which those are good variables, and then sort of remembering we're in charge. Like, we get to be our statistical programs don't get to boss us around, right? Our statistical programs will tell us what we ask it to tell us. But if we've made an error, we need to be able to go through and recognize, say, hey, this isn't a reasonable answer, sort of make sure that we're thinking flexibly and critically about stuff. Okay? Cool. All right. I'm going to jump through and I'm just going to introduce first couple of slides here, just in the last 15 minutes. You get a head start on stuff. We'll end up being behind schedule at some point in the semester, so we'll use this to gain some traction. But what we want to do is take some of the stuff that we've talked about today and start taking this into sort of the realm of some applied statistics, talking about distributions, probabilities, and then we'll finish up with some confidence interval stuff, which will be important and crucial. You want to have a good handle on that. Okay. So again, we talked about here in this last deck of slides, if I've got a mean and standard deviation, starts to give us important information about the magnitude of any individual observation. Okay, what we can do, right, is if I'm just looking at a raw score and I have mean and standard deviation, I can start to sort of infer some stuff, right? But I have to do some mental gymnastics about some things. And a single raw score doesn't give us a whole lot of information with respect to the rank relative to other scores in the distribution, the extremity of the magnitude, or anything about the probability observing some value relative to the rest of the distribution. Okay, And so what we can do is we can start to take with the mean and standard deviation, we can start to create standardized scores, okay? And our standardized score starts to give us a metric for communicating information about individual observations. Standardized score is a nice parsimonious statistic. A z-score will tell us information about the score, about the mean, and about the standard deviation, all in just one single value. Okay, and so if I'm interested in looking at the position or rank of a score relative to other scores in a distribution, or assuming a normal curve, I can start to get information about how likely or how probable finding a value of a certain a score of a certain size is going to be given known information about my distribution. Okay, so again, this will be a nice relative, or this is a reasonable example people tend to sort of be aware of, right? If we're thinking about IQ scores, right, in the measurement of intellectual ability, we tend to think about IQ scores as existing on a bell curve, right? We've got a natural curve where we've got, by definition, average score in the population is 100, standard deviation is 15. Okay, we know that scores, because we've created these measures to do this, we're expecting a normal curve. Average is going to be right about at 100, and sort of the average distance we would expect from any randomly selected score in the distribution. If I just pull up, Robert just pulls out a random person out of the distribution, he's expecting that person to be on average about 15 points from the mean. Okay. So what we start to do with our z-score is we can take those scores and start to use them to form a distribution where the mean is no longer whatever the mean of our raw scores are. We're going to set the mean to be 0 and the standard deviation to be equal to 1. Okay, there's mean of 0, the standard deviation 1. These are the defining features of a z-score distribution. All right, and so our z-score is two pieces of information. The value of the z-score, this is going to tell us the number of standard deviations from the mean. I want everybody to unmute yourself right now and say the value of the z-score is the number of standard deviations from the mean. Everybody do it. Do it.
The value of the z-score is the number of standard deviations from the mean.
Beautiful. Robert, I didn't hear you say it. There was no bass in that.
I was hoping you would catch me. No. Indicates the number of, or value indicates the number of standard deviations from the mean.
Okay. This is going to be important. I think about this whole thing as like a Karate Kid moment where like there's a paint the fence, wax the deck business like that. This will start to become important as we start to get into effect sizes and things like that. But your z-score, the value is just telling you the number of standard deviation units from the mean of that score, and the sign just tells you the position. Is it above the mean? Is it below the mean? Okay. So if I'm looking at sort of this distribution, this is easier to do when we're all in a classroom and you can point to things, right? But if I'm, it's a fairly easy task. A z-score of 1 is right here, right? Z-score negative 0.5, right here. Z-score 2.5, here. Negative 1, here. We could point to an infinite number of z-scores, right? But if we're assuming a natural distribution of this, what starts to happen is that our z-score starts to tell us the likelihood of obtaining some certain value, right? If we start to get things out here, z-scores of 2, 3, 4, negative 2, 3, 4, those are very rare scores. We're not likely to randomly select someone out there, right? But as we start to get stuff towards the middle, pretty likely. That's where the bulk of the distribution is existing. Okay. So our formula for z-scores, easy, easy, easy. We're just taking, to calculate a z-score, we're taking our observed score, subtracting the mean of the distributions, and dividing by the standard deviation. Okay. This is just a ratio. We're going to deal with ratios all semester. We've just got a deviation score divided by a variance estimate. This is going to give us 99% of our test statistics. Okay. So, if we go, Allie, if I've got a mean of X or an observed score of 12, a distribution mean of 10, and a standard deviation of 2, what's my z-score for this individual?
Should be 1.
It's going to be 1, right? 12 minus 10 divided by 2. 2 divided by 2 is 1. So I've got a z-score of 1 here, right? Is that a very common or an uncommon score in this distribution, assuming a normal distribution?
Should be pretty common.
Should be pretty common. All right. I'm going to stay with you. All right. What do we got? We got an observed score of 8. What's our z-score going to be now?
-1.
-1, right? So we've got someone who is exactly a standard deviation below the mean. What about 11?
Like a half.
Yeah. Almost. Oh, no. Yep, you're right. Yep, you're right. You are. Yes, I thought it was negative.
Oh my god.
Yeah, no. Haha, you're my student. I'll sort of put you through anxiety drills, right? No, you're exactly right. So we got someone who's about a half standard deviation above the mean, right? So very quickly, if you just say, oh, here's X is 12, 8, or 11, I don't know much about that. But if you tell me a z-score of 1, -1, and 0.5, all of a sudden I have much more information that I can use and make inferences about that individual, okay? Someone with a calculator, real quick. Who's got a calculator? Riley, you do. Okay. Let's say I have an observed score of 7. Mean of my distribution is 34.6. I've got a standard deviation 8.2. What's my z-score?
I got -2.1.
Okay, perfect. -2.1. Okay, Riley, is that what am I inferring about that? What can I infer about that score?
That score is a little bit over 2 standard deviations from the mean, or yeah, a little bit over 2 standard deviations, like below the mean.
There we go. About 2 standard deviations below the mean, right? And that direction starts to make a big difference, right? So we've got someone who's actually starting to get pretty extreme on the low end of whatever it is that we're measuring here, right? Again, assuming that we have some sort of normal distribution. So z-scores are easy to go through and calculate. And any type of standardization that we do, whether it's test statistics, effect sizes, it's almost always going to follow this basic ratio format. Okay, and so just having a basic understanding, like a lot of times when we start talking about formulas, people's eyes will glaze over, right? And you just say, oh, that this is, I'm just going to plug in numbers. Try and avoid that urge. As we're going through all this, the mathematical formulas carry an intense amount of information about what's going on here, right? If we look at this z-score formula, we're taking a deviation from the mean and dividing it by expected variability is going to tell us how far or where we're at in terms of stuff, right? Ali, if I've got this x of 12, mean of 10, sort of that example that you were going through, what happens to my z-score if my sample variability isn't 2, if it's 5? What happens to my z-score?
It gets smaller.
Yeah, it starts to get a lot smaller, right? If I increase the variability of my sample, my resulting score starts to get smaller. What if my variances or my standard deviation is 0.5? What happens to my z-score?
Sorry, what?
If instead of 2, my standard deviation of this distribution is 0.5, what happens then?
Bigger.
Starts to get bigger, right? And so almost all of the test statistics that we run through this semester is based on this format, right? Where you've got some sort of deviation score at the top, and then you've got some measure of variability. As my variability increases, what happens to my test statistic? Or as my variability decreases, my test statistic is going to go up. Oftentimes, that's what we like. As our variability increases, our test statistic goes down. So just looking at these formula and thinking about what happens when I divide a bigger number or a number by a bigger or smaller denominator, how does that impact things, is going to start to help you sort of get a good conceptualization of potential impacts of different things that can happen within these data sets. Okay. All right. Graphing z-scores, this is pretty easy, straightforward. We have here just sort of a raw distribution. Here we've got my z-scores, here's my raw score. And so here at x17, if I assuming a mean of 34.6, standard deviation of 8.2, my x of 17 is negative 2.15. It's kind of right down here, right? Okay, yeah. And so in our the problem set that you'll work on for this, not the one that you have right now, but the next problem set, we'll be using a lot of sort of mapping things out as you start to get a handle on transforming things back and forth from standardized scores. This type of format is also often a nice thing. I'll have you do this just so you can start to see where things are falling on stuff. Okay. Questions? All right, folks. Thank you for hanging in there with me. It's always like, oh, we got 15 minutes. Maybe this guy will be cool and let us go. No, this guy's never cool. You shut up, CJ, as he's laughing in the background. I like how my GA turns on his camera just to show everybody he's laughing at me there. But any questions before I let y'all go? All right. You folks are crushing it. Got this next, our first problem set will be due not this Friday, but next Friday at noon. But do make sure to go through, start getting an early start on it, work through stuff, get in touch with CJ or I if you have questions. Again, work together, bounce ideas off of one another. Just make sure that you're doing your own write-up and your own explanations and things along those lines. And then, yeah, when we touch base next Wednesday, if you have any questions or anything like that, we'll touch on those at the beginning of the class and then take things from there.